Hello. So in today's lesson, I want to go over some real-world applications of quadratic equations. Um, so first, we're just going to start out with an example. So quadratic equations have many uses in the real world, and one of the most prominent ones is projectile motion. So projectile motion involves describing the path of an object that is subject to the force of gravity, which I guess all of us are here on Earth. So it's really useful to us because we could do things like say, okay, if I throw this marker in the air, I can use quadratic functions to see what its trajectory is and see what its height would be at different points. So that's kind of the main application we're going to explore for quadratic functions, but of course there are many others, so we'll delve a little bit into those as well. So we start with an example. A ball is thrown in the air, modeled by the equation h of t is equal to negative 32t squared plus 65t plus 6, and I'll add in h of t represents the height in feet, and t represents the time in seconds. So first off, we want to just look at our equation and just nail down really what each variable represents. So h of t, this entire thing represents the height, whereas just the t represents the time. So depending on what information we're given in the problem and what we want to solve for, we're going to substitute in a value for either the time or the height. So we're going to substitute for either h of t, this entire thing, or just the t values. So we'll start out by saying a common question is, what will the ball's height be at 1 second? So if we want to find the ball's height at 1 second, we're given a time value. So we're given t, and we want to substitute in that time value into our equation. So we're going to have h of 1, which 1 is the time, remember, is equal to negative 32 times 1 squared plus 65 times 1 plus 6. And then we'll just solve this string of additions. 1 squared is just 1, so we'll get negative 32 plus 65 plus 6. Negative 32 plus 65 is equal to 33 plus 6, which is equal to 39 feet. So we know for a fact that given this equation, if we throw this ball in the air after 1 second, it's going to be 39 feet in the air. So that's about 4 stories high, so about 40 feet. And that is how you would solve this question if you're given the time. So note that we're solving for h of 1, and we're simply substituting 1 in for each t and seeing what our answer is going to be. So suppose we're asked, what will the ball's height be at, say, 1.5 seconds? So this one is a little bit trickier, but instead of 1, we're just going to put 1.5 into the equation. So h of 1.5 is equal to negative 32 times 1.5 squared plus 65 times 1.5 plus 6. So for this equation, we're going to want to get out the calculator. Luckily, I have one right over here. So I'll multiply negative 32 times 1.5 squared is equal to negative 72. 65 times 1.5 is equal to 97.5 plus 6. So if we add these up, we get that's equal to 31.5 feet. So you can see after 1.5 seconds, the ball is lower than it was after 1 second, so the ball is going down at 1.5 seconds. So you'll also notice the numbers aren't always going to work out really nicely, because when we're going into real world scenarios, nature doesn't always work in like really neat numbers. So just be aware of that. So that is how we solve these problems if we're given the time. So suppose instead of that we're asked what times will the ball be at a height of 20 feet. So this time we're given the height, so we're given h of t, and we want to solve for t itself to find the times. You notice I have an s here, because when we throw something in the air, so say I throw this in the air, it's going to be at this specific height twice during its trajectory. So again, I'm going to throw it up in the air, it's going to pass this point once, and then it's going to pass it again. And like I've done a couple times, you can just watch it and see that it's going to be at each point in its trajectory twice, other than the very top. So this time, we're given h of t, so we're going to plug in 20 for this whole thing. So we're going to get 20 is equal to negative 32 t squared plus 65t plus 6. So now instead of simply adding 3 terms, we have to solve the quadratic equation. The good news is we already know how to do that. So generally with equations like this, where you're going to have kind of messy numbers like this, it's best to just use the quadratic formula to solve. So to start out, we're going to subtract 20 from each side. We're going to get 0 is equal to negative 32t squared plus 65t minus 14. So something I'm going to do just to make the numbers a little bit simpler is I'm going to multiply both sides by negative 1, because that's going to give us the same answer. And a reminder, I can do that since negative 1 times 0 is still 0. And now I'll use, I guess, our favorite formula. The answers are going to be equal to x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So we have a, b, and c. Our x is going to be equal to 65 plus or minus the square root of 65 squared minus 4 times 32 times 14, all divided by 2 times a. And then we're just going to plug this all into our calculator. So we get, first I'll do the plus case. So we get 65 squared minus 4 times 32 times 14, take the square root, and that's going to be equal to 49.3. This is going to be equal to 65 plus or minus 49.3, all divided by 64. So if we add that, so plus 65 divided by 64. One of our answers, sorry, this should be a t, is t is equal to 1.79 seconds. Or, if we do the minus case, we have 65 minus 49.3 divided by 64 is equal to 0.25 seconds. So that would be the answer for when the ball is at a height of 20 feet. And again, it makes sense that we have two answers because the ball is going to be at this height at, say, 0.25 seconds. Then it's going to go higher. Then gravity is going to keep doing its work. It's going to move it down to here. And after 1.79 seconds, it'll be at that same height again. So these are two examples of problems you could get. There is, I guess there's a lot you could do with this equation, but that would be delving, I guess, a little bit further into physics than we want to get in this class. But one more question that we could be asked is we could be asked to, I'm just going to move this over. We could be asked to find the maximum height of the ball. And again, our function is h of t is equal to negative 32t squared plus 65t plus 6. So we see maximum. First, we want to confirm that this function is indeed going to have a maximum height. And to do that, we can say, okay, we have negative 32. We have a negative here, so that means that our quadratic function is going to have a maximum. Since a is less than 0. So now how do we find that maximum? So we've already done this with just lots of basic examples, but we haven't applied this to a real world problem yet. So first we want to find the axis of symmetry, which is given by the equation x is equal to negative b over 2a. Negative b is equal to negative 65 divided by 2a, which is 2 times negative 32. It's going to be equal to negative 65 over negative 64. I'm going to plug that in our calculator, and we get 65 divided by 64 is equal to 1.01. Once we find our axis of symmetry, we want to plug it back into our original function, and that will give us the maximum height. So we'd say, what is h of 1.01? That's equal to negative 32 times 1.01 squared plus 65 times 1.01 plus 6. I'm going to put that into our calculator. And we are going to get that is going to be equal to 38.64 feet is going to be our maximum height. So again, when we're asked this question, we just take our original function, find the axis of symmetry, and then plug it into the function. And actually, now that we have the axis of symmetry, now that we have the maximum height, which is the maximum value of the function, we can actually graph this. So if we build, so say time is here and height is here, I'm just going to go through this pretty quickly. Because we have a couple points that we know now. We know our maximum is going to be at the point, which is also our vertex. It's going to be at the point 1.01, 38.64. So, got up there. then we also have the point, so we know that the ball is at a height of 20 feet at the time 0.25. That's from our previous calculation. And 1.79. And then all we have to do is connect the dots, and we get an equation for the trajectory of our ball. And just one more just kind of cool thing is you can kind of confirm that quadratic functions govern projectile motion by noticing that if you throw something in the air, the path it takes is going to be a parabola. So that's just a cool kind of side physics thing. So that will conclude our study of quadratic functions with these real-world examples.